I think we're now good to start. We've had our break before we started, so please get ready for 3 hours of content in one go without even a break to go to the toilet. Just joking, we will take some breaks in the middle. And if you need a break because you feel you're getting all tired, please let me know. We can break quickly so that everybody can stretch their legs, because 3 hours talking without breaks is just too long. In Australia, lectures are only 50 minutes.
It's going to be very hard for you rather than for us.
Certainly the first one, I'll be talking about functional integration by digital light projection. That's all my own work, so that's easy talking about. Later in the day, I'll get to a lot harder things, because I've tailored it a little bit towards making of nanoparticles in agriculture and the areas, and as well as organ on a chip. And they're all areas that I'm not quite familiar with, but we'll get there. So the work that I'll be talking about, I had a really, really good student, Harry, and he's getting married in 2 weeks' time, and he invited me to go to the wedding. So I'll be attending my first Indian wedding ever, which I'm really looking forward to. But Harry was an excellent PhD student, mechanical engineer by background, and managed to familiarize himself with the chemistry, with polymer chemistry, polymerization reactions, and did really well. So he's now doing a postdoc in Abu Dhabi and working very closely with the industry, has got some IP that's about to be licensed, so he's doing well. So what we'll be talking about is multi-material digital light projection in presence of a porogen. We found out that the chemistry that is used for digital light projection 3D printing, it is just an acrylate chemistry. And in a previous life, I had worked with the synthesis of polymer monoliths. At that stage, that was really a hot topic to make columns for liquid chromatography. And one of the reasons they were so attractive for HPLC is because even in nanobore columns, they had a very low flow resistance. We then took the same approach of taking a highly porous, low flow resistance scaffold, but then use it for heterogeneous catalysis. So we functionalized the polymer monolith, put a ligand on top with some palladium, and then we're able to do palladium in these flow-through microreactors. Moving then years later into the digital light projection, I'm like, I've seen this chemistry before, I know this. And at the same time, we had the need to start making porous membranes. We like functionality. The first step in sample preparation quite often is removal of particulate matter. And porous materials then are the first thing that jump to mind. So the idea was, could we adopt the chemistry that we use for making the porous materials to do either heterogeneous catalysis or separations on? Could we use that same chemistry, that same concept, in 3D printing? And the answer there was yes. And what we realized, that there were 2 different areas that we could play with in creating the fine-tuning the material properties. One was with the resin chemistry. What is the monomer or monomers that you're using? What is the porogen, or typically porogens, the solvents that are not participating in the reaction, but take space and therefore create voids that are ultimately leading to the porosity? What is the role of the photoinitiator and the photoabsorber in this effect, and how can we, so they are the chemical ways of fine-tuning the porosity. And then are the printer settings, which are the exposure time, the light intensity, the layer number, and the layer height. So throughout Harry's work, he explored these different parameters and then applied it to some different applications, going one step at a time. So the first test was, can we actually, by adding a porogen to a normal 3D printing resin, can we make a porous material? And we did that with 2 sets of monomers. We tried that with hydrophilic monomers. PECDA is, as we've already heard yesterday, with the digital light projection lecture. We already heard that PECDA is a very nice hydrophilic monomer. So we added porogen, in this case methanol, and we found that actually we indeed could create flat sheet membranes when we designed them to be. They had a thickness of about 200 micron. We also could print them 100 micron, but we couldn't get them off the pick. So the pick is the metal plate that it's sitting on at the moment. So we needed to have a two-layer print to get the structural rigidity so that we actually could take it to our equipment for characterization. But we could repeatedly just print membranes that were kind of the size of 2 microscope slides. We then used a fluorinated resin, and that worked as well. And indeed, if we get a fluorinated monomer, then we get a hydrophobic membrane. And here you can see the thickness again was 200 micron to have the structural integrity for us to be able to lift it up the build plate. And the pore size, we characterized that with porimetry, was around 300 nanometers. And here we can see some droplets showing that indeed we have hydrophobic properties. So we created a little flow cell to see if the membranes actually could be used for filtration. Here we've got a setup where we've got a sample, an input coming in, which was a suspension of some microparticles in water. We have a flow of water coming out that goes from the top of the membrane, and we've got the bottom of the membrane. And you can see the permeate, the solution that has gone through the membrane, doesn't contain any particles, whereas the retentate, the liquid that hasn't passed through the membrane but just flown underneath, contained all our particles. So we were able to separate, filter out particles, and end up with a particle-free solution using our 3D printed flat membrane.
Characterization was done through?
Just microscope and counting the beads. Okay. So collect the permeate, collect the retentate, place a droplet of that solution on a microscope slide, and look under the microscope to see in a grid. You can see particles, and then you can calculate back to how many particles there were. So here we use the fluorinated monomer, which has got a funky name. Use cyclohexanol as a porogen, because one of the important things about the porogens is they need to be the monomer and porogen need to be miscible. So we use cyclohexanol, which mixed well with the F13F001, and then 3D printed the porous membrane. Here we can see the droplets beading up. The contact angle is 148 degrees, which we are still sad about, because materials are considered super hydrophobic if the contact angle is over 150 degrees. So it is nearly super hydrophobic, but we couldn't get it to cross that barrier. So we just still have to only refer to it as a hydrophobic system. What we did here is to print the device with a print pulse print approach that we already talked about. So here in black we printed the flow cell. We changed the resin formulation to this one. We printed the 2 layers to have our 200 micron thick membrane. In the design there was a little spacing left in the first layer for the membrane to fit in. And then we continued with the print so that we could get an enclosed fluidic flow cell, fully made by 3D printing, that we just had the fittings to attach the tubing to and could use for separation science. So we tried a couple of different compositions of this material. We found that if we decrease the amount of porogen, we decrease our pore diameter. It was even only 143. And we could see that if the more porogen we had in there, the more hydrophobic our material became. But yeah,
How this characterization was done?
A porimeter. So it is an instrument that applies increased pressure and then measures the flux through the membrane, and does that with fluorinated solvent first under wetted conditions and then with nitrogen.
What's the name of the equipment?
Porimeter.
Porimeter.
So it is a standard piece of equipment used to measure the pore size in membranes. So there's 2 different ways of doing that. There is mercury intrusion porimetry, and that measures all the pores, also the ones that don't go from one side to another. So it increases the pressure and looks at the volume of mercury that you can squeeze into the pores. Whereas the perimeter applies pressure over the membrane and measures at what pressure how much flux gets through the pores. So the difference between the two pore sizes is one has got overall porosity, having the sum of the pores that go through the material and the ones that are just dead end street. And in this way you measure the pores that allow that support any flux. So we use this for phase separation. So we had, in this instance, we had a two-component mixture existing of ethyl acetate and water that are non-miscible. We used a simple T-piece to create droplets. In this instance, we again use Teflon tubing. Teflon is hydrophobic, so which becomes the continuous phase, the water or the ethyl acetate?
Water?
No, we've got a hydrophobic tube. The hydrophobic tube prefers to be wetted by the solvent over water. And the continuous phase is always the one that wets the surface.
Then it will be.
Yeah. So our water is our dispersed phase.
Okay.
So we've got blue droplets and the ethyl acetate is our continuous phase. So we connect to a dual syringe pump, a T-piece, create the droplets. Droplets were introduced into the membrane. The hydrophobic membrane would have passed the aqueous or the organic phase. Organic. So the ethyl acetate would pass through the membrane, whereas the aqueous phase, the pressure was too high to pass through the membrane and would come out. So we could phase separate the water and the ethyl acetate using a hydrophobic membrane, where our permeate contained our organic phase, the ethyl acetate, whereas our retentate was the water, because the pressure to allow the water to move through was too high. So we had to balance the pressure a little bit, where at some if there's no back pressure applied at all, we didn't get any separation. Initially we got still a little bit of ethyl acetate coming out in our retentate, and then after optimizing the pressure coming in from one side and being pushed back from the other, we managed to get the right pressure across our membrane that allowed all of our ethyl acetate to go through and have no water in the permeate, no ethyl acetate in the retentate. So it was a little bit of trial and error, and here you can look at a couple of different pressures where we changed the back pressure and looked at what the flow rate was coming out and how clean that was. So we defined some optimal ranges where we could use this flow cell for the phase separation of water and ethyl acetate.
Here the equipment used was?
We had flow sensors, so the pressures were measured with pressure sensors that we put in the reservoirs. The flow was measured with a flow sensor that we bought online. So there are pressure controllers that you can buy with little flow sensors.
So then plotting was done in the Excel and all?
Yeah. So with the idea of doing functional integration, we looked at optimizing the chemistry and creating, if you remember us yesterday talking about the size mobility trap, the next application that we worked on was trying to see if we could create a size mobility trap with two different porosity membranes, knowing that through optimization of the resin chemistry, we could create different porosity membranes. So this is the device that we tried to develop. We have two different reservoirs, or three different reservoirs. We've got two large reservoirs, one to contain a sample, thermal lysate of E. coli, one to contain buffer, and one to contain our extract. We would like to concentrate the sample, extracting it from our sample reservoir. We would like to concentrate our analyte into a small volume. Therefore, the sample collection chamber here was designed to be really small. We looked at the resin composition to see how we could tune the pore size. And what we found that if we want to have a significant, like an order of magnitude difference in pore size, doing that with a photoinitiator concentration is really difficult. You can go from like 200-300 nanometers to 700-800 nanometers, but not really an order of magnitude in size. But if you start manipulating the porogen, you can actually get significant changes in pore size. So we created 2 different membranes in the print process. For one membrane, we used 70% porogen. So we had a PECDA resin with 70% methanol in there. And we created a membrane with large pores, from memory somewhere around 300 nanometers on one side. Then we cut down the porogen concentration to 50% and printed the other membrane with that. And that membrane had pore sizes we could no longer measure, but still allowed us to carry a current. And therefore we assumed there would be some transport of small inorganic ions coming through. Because if we took any less porogen, we could no longer measure a current. So we don't exactly know the pore size because the perimeter said it's non-porous, but we could still measure electrical conductivity, which automatically means that there's transport of electrons and small inorganics. So we made this device by print pros print. So we printed the bottom yellow part, first reservoir, paused, exchanged for the resin containing 70% methanol, created membrane number 1, got back to the original resin, printed a small analyte extraction reservoir, exchanged resin to our narrow pore size membrane, printed that membrane, and then exchanged back to our resin that didn't contain any porogen, and printed the rest of the device. So the macroporous membrane separates the chamber number 1 with the lysate and the chamber number 2, which was the extraction chamber, and had a pore size about 300 nanometers. So our aim was here that DNA could be electroextracted across this membrane, but proteins and cell debris wouldn't. Our other pore size was, our best approximation is around 20 nanometers. We would like to this membrane to stop the migration of DNA, but still allow sodium and chloride to get through to carry our current and establish our electric fields. As already said, the bottom of the extraction chamber here, chamber 2, was really shallow to minimize the volume and to enhance the concentration enhancement factor that we could realize using our electroextraction. We've optimized that resin exposure. Let's see. Okay, so we looked at the different properties, how we could influence the porous properties of the material. So if the exposure time per layer is reduced, here we go from 120 seconds to 30 seconds, we can see an increase in our pore size and also a broadening of our pore size distribution. The density of our resin decreases as well, and we get a decreased strength and lower breathability if we really want to get any smaller pore sizes. So we like the smallest pore size there that we had. Then we looked at the chemistry, we looked at the photoinitiator concentration. If the photoinitiator concentration increases from 1% to 4%, again 1% here, we can see the more photoinitiator, the smaller the pore size. Our target, we thought, for allowing DNA and not stop the proteins was around 300 micron. So we selected that the composition with 3% porogen to create our first membrane. And here you can see some SEMs of the materials as they form. And you can see if you've ever seen SEMs of polymer monoliths used in HPLC, it is the same cauliflower-like structures that are evidence of the fact that during photopolymerization, we get the growth of our polymer chains, and at a certain point these polymer chains phase separate and crash out of solution and form a solid. And that typically is a process that works in these mesoporous cauliflower-like structures. Really, really beautiful to look under in an SEM. So we then indeed, as I already said, looked at the amount of porogen. At 50%, we think the pore size was around 20 nanometers, and we had a current. When we dropped the porogen content further down to 45%, there was no more current, and we couldn't measure a pore size either. So that was all the work that was done by Harry, one of my students, but he was a mechanical engineer, and doing DNA amplification, teaching him that seemed to be a step too far. Luckily, I had another really nice student in my group, which is Soo-Min Lee, and her PhD was on simplifying the chemistry for lysis and DNA extraction. And for all the work that she did, she had to validate all the results with PCR. So we called in the help of Soo-Min to look at the extract that Harry had, and Soo-Min put it into the PCR and then helped conducting the analysis to quantify the DNA coming out. So what we did in the assay was that we pipetted the E. coli lysate into our sample reservoir. We applied a potential difference. DNA is negatively charged, so it will migrate towards the positive electrode. First membrane was the one with the 300 nanometer pores, so the DNA would have no problem passing that first pore. Then we had our fine, around 20 nanometer pore size membrane, and the DNA didn't fit through. Which means that even though there was a driving force of the DNA to go to the TBE buffer reservoir, it couldn't pass through. Yet we still had a large buffer reservoir here to provide us with significant buffering capacity. Because one of the things we realized that when we had our electrode in the same reservoir as our extract, we got so much H+ being formed that we significantly changed the pH of our solution, which then interfered with our amplification. So having a large reservoir here was purely there to provide us with the buffer capacity to absorb all the protons being formed due to electrolysis as a result of the application of an electric field over our extraction cell. Our E. coli lysate was in buffer as well, so the hydroxides generated there would be comfortably mopped up as well. Here are the results, and one of the things with PCR is what you measure is the CQ value, which is the number of times that you need to thermocycle to get over a certain threshold value. If you start off with a high concentration of DNA, that means that you don't need to go through a lot of cycles to get over your threshold. So a low CQ value means that you had a lot of DNA in your sample. The more cycles you need to amplify your DNA, the lower the start concentration was, because that is the number of cycles that you need to go over the threshold. So a high value in this graph means there was very little DNA to amplify. A low value means there was a lot of DNA to amplify. So that's a little bit the opposite to analytical chemistry, because things like absorption, high is always better. With PCR, low is always better. It takes a little bit of rethinking. The other thing about the CQ value, because DNA is a logarithmic process, an increase in CQ value actually means a factor 10 more DNA. So whereas the numbers go up linearly, please be aware there's a significant difference between a CQ value of 20 or 20 to 23 in the amount of DNA that is present. So we optimized the DNA extraction on two different parameters. First, we looked at the potential difference applied across the cell. So we increased the potential difference from 2.5 volts to 15 volts. And we saw that we got a decrease in CQ value, so an increase in DNA in our extract when we increased our potential difference. The other parameter that we looked at was increasing the time. So we did this for 5, 10, 15 and 20 minutes. And we could see that we got a decrease in CQ value, so also an increase in DNA concentration if we extracted for longer. No big surprises there. If you have a higher potential difference, you get a higher number of ions moving, so you extract more DNA. If you do that for longer, you get more as well. But we still found that there was an optimum, because above 12.5 volts, we got serious problems with the electroosmotic flow, and we started seeing significant differences in liquid height in our reservoirs because we were pumping our liquid from one reservoir to another. The other thing that we saw, that after about 20 minutes our devices were uncovered, we actually lost a lot of our water due to evaporation. So we said no more than 12.5 volts. Let's stick with the 15 minutes because we get increased error bars and no real significant gains anymore, because we get evaporation and then we get big changes from one day to another. So under optimum conditions, the CQ value ended up just over 17. We then looked at the recovery rate of both the DNA and the protein, and we found that we could remove 73% of the protein. So we did that using a nanodrop instrument, and we could see that our recovery rate went close to 95% at the 15 minutes.
Which instrument? Nanodrop?
The nanodrop. So the nanodrop is an instrument that measures the ratio in absorption over, I think it is 260/380. So it gives you the ratio protein to DNA in a solution, in a small droplet. So it gives you a ratio of absorption at two different wavelengths, which is one of the analytical approaches that molecular biologists use to test if they've removed enough protein and have sufficient DNA to start amplification, or if they need to dilute. So we looked at the relative extraction efficiency over time, and we could see that again under our optimized conditions, we were over 90% efficiency, and a commercial kit that we could buy off the shelf that most molecular biologists use to extract their DNA was 93.7. So we were not significantly different in our extraction efficiency compared to commercial kits. We looked at the CQ value when we had increasing amounts of E. coli in there, and here you can see that over a concentration range, if the concentration of E. coli increased, we could see a nice decrease in our CQ value. So we had a quantitative test there with the PCR to quantify E. coli in the lysate. So in principle, this could be used for the detection of E. coli in a range of different samples. The next application that we tried to use for our membrane integrated devices was for chemotaxis. So for those of you that are doing any biological projects, chemotaxis is the process that microorganisms, but perhaps people, are also attracted to certain chemical cues. So if you're hungry and you walk past a bakery and you smell freshly baked goods, you want to go there. Microorganisms do exactly the same thing. If they smell a food source, they want to go there. If they smell something that's bad for them, they don't want to go there. And we looked at chemotaxis with little zebrafish embryos, as well as planarians. Planarians are little worm-like creatures that are present in lakes. So chemotaxis is directional. If you really want to go somewhere, if it really smells good, you go there. If it really smells bad, you move in the other direction. Whereas chemokinesis is just a movement in random direction. So we developed a little test device about the size of a microscope slide, where we wanted to look at the role of a chemical gradient to different microorganisms. So we have the bulk of the device here. We again used print, pore, print, and we integrated two different membranes with a pore size of around 400 micron. The reason that we needed a membrane is that we knew that the planaria really liked a liver extract. A liver extract contains a lot of cells and debris, and if you want to study your planarians in presence of the liver extract, you can't see your planarians anymore because your solution is too dirty. So here our plan was that we would have a solution or a reservoir that we could pipette our liver extract in. Our molecular components would be diffusing through the membrane and establish a concentration gradient in the flow cell. If the planarians would really like the chemoattractants, they would swim that way. If they didn't care, they would equally distribute. If they would really hate the liver, they would all be sitting at the other side. So we printed the device again using the print pulse print approach, where we print the first part of the device, change the resin, print the membrane, and then print the remainder of the device. And then the second one gets printed. So here you can see some SEMs that still we have this cauliflower-like material. We control the membrane properties here by looking at the exposure time, using the layer thickness. So here we can see that we set our printer layer thickness at 200, 150 or 100 micron, and could see that the thicker our layer thickness was, the longer the exposure time, with the higher the light dose, and therefore the smaller the pores of our membrane. And again, these observations agreed with a decrease in porosity and an increase in density of the porous materials that we formed. We found out that we got the narrowest pore size distribution, as well as the best, the lowest amount of breakages in our membrane if our membranes were composed of 300 micron thick layers. So we took the layer of 100 micron, but then repeated 3 layers, which tightened down the pore size a little bit as well. Once we had the devices, we started looking at what a small molecule would do and how long it would take to establish concentration gradients. So here you can see a couple of devices in the setup. I think it's nice to see here that there's no rocket science in the way that we do our experiments. We've got a Petri dish here, a desk light, some graded paper so that we can, from our photographs, derive distances. And we had a stopwatch to measure time. We filled a fluorescing solution into the top components, and we waited for increasing numbers of time, and we could see indeed a fluorescing front progressing through the membrane to the other side. So we knew that over time a concentration gradient would establish, and could anticipate that if this is for a small molecule, around 400 daltons is fluorescing, proteins will take a little bit longer, small inorganics would take a little bit shorter. So after 15 minutes, we could see the first fluorescence showing up in the chamber. So it would take a little while for a visible amount of fluorescence to actually have migrated through the membrane. About 30 to 40 minutes, small molecules are halfway. And after an hour, the whole chamber has got kind of a homogeneous concentration. And we wouldn't be able to really study chemotaxis behavior anymore. So with this, we limited our operation behavior for the experiments to a period of 45 minutes. So here we've got the experiment done with little zebrafish. Zebrafish get a little bit scared if you handle them. So we had a device ready with our sample not introduced yet. Put a little cylinder there so that the zebrafish were no longer stressed by the time that we started the experiment. At T is 0, we could lift out this little cylinder, and the zebrafish could start swimming in any direction they liked. And if you see the green dots are the zebrafish that we could count at the chemoattractant site. The red ones are the ones that we found at the water site. And you can see that the time that each of the zebrafish spent at the chemoattractant site was significantly higher than they spent at the bottom of the device. Here the heat map perhaps shows it a little bit better even, where blue means there's hardly any time of the zebrafish spent. Red means that they're around there all the time. So the zebrafish were all the time looking for nutrients in the top part of the device. We did the same thing then with our planaria, with our liver extract.
What's the green and the
It is a color scale for visualizing, so it's a heat map. And in the heat map you can define the frequency of visits. So blue means that we've got very few visits, red means that we've got a lot of visits. So we created a heat, so we determined the location of the planarian and then gave a color value to each of the frequencies, and that then allows you to visualize it in the form of a heat map. So it is a way of plotting your data when it becomes multidimensional. You can't just have a calibration curve in a straight line. Because we have a number of different planaria and a number of different devices, we decided that a heat map was the best way to visualize the richness of the data that we had, because it gives you an additional dimension compared to otherwise we would have needed lots of different graphs. So we actually started off graphing, and then the biologist says, why don't you use a heat map? And then we went for that approach.
All these things have been done in the clean room?
No,
No.
just normal lab on the bench, just a standard laboratory.
Okay.
Devices are the size of a microscope slide. So we printed the devices in our lab and then took them to our collaborator that's got the zebrafish tank and everything, and we actually did it in his lab.
Okay.
Because that was close to the zebrafish, so we could just take them out of the tank. So with the planarians, again, they sit in the little cylinder. After 15 minutes, they are de-stressed, so we can release them. And then after 30 minutes, you can see them swimming here. They are present close to the chemoattractant. You can see the brown gooey stuff here on what the liver extract actually looks like, which makes it then understandable that if that's around, it is really hard to find these planarians all back. And you can see towards the end of the experiment, we get a relatively homogeneous solution. So we found an increasing amount of planarians also towards the bottom of the device. So here we've got the heat map of the frequency where they spend on all sides. And we can see that most time was spent for the planarians at the site of the liver extract, which confirmed our hypothesis that the liver extract is a chemoattractant.
How come they are, kindly go to the, how come after 45 minutes they are randomly moving?
Yeah, they're just little swimming creatures. They're little worms that swim.
No, but after 30 minutes they are towards the attractant side, no?
Yeah. So they prefer to swim here. So they go on a random walk. If it smells good, they continue swimming. But then once they've eaten, they may decide to just see if there's anything out there.
Okay.
So they swim all the way around, and at any point in time, most of them are close to the food. But once they've eaten something, they may still think there may be more food somewhere else. So they go on a random walk, and then as soon as they pick up trace, they swim back again.
Right time for detecting is 30 minutes then?
Yes, because after that, as we'd seen,
Can you quantify them that way?
you can just count them.
Okay.
So here we can see after about 30 minutes, we are halfway. So now you can still say something. If you wait any longer, your chemoattractant will be everywhere, so your results become meaningless.
Okay.
So that worked with the chemoattractants. So we now have understood that we can play with both the resin chemistry and the print parameters to control the porous properties of integrated membranes. If we look at functional integration in 3D printing, however, we have the post-print integration, which is stick a membrane off after, print pros print. In 2017, we managed to do some in-print with FDM, fused filament. What we really want to do is do in-print integration of membranes using DLP. So that was the original start of Harry's PhD, to see if we could get there. And indeed, after we had done all this work developing the porous resins, we managed to find a way where we could, without any resin exchange, so without the need for print pros print, we could actually print a porous membrane inside a microfluidic device. Because what we found is that if we could apply a grayscale mask, so we could dynamically change the intensity of the light during exposure. If we have no grayscale mask, we expose at full intensity, and we optimize the exposure time so that that would allow us to create a dense material. If we then increase the intensity of a grayscale mask, from a grayscale mask of 45 to 75, we have a decreased light intensity when we do the polymerization, which means that our polymerization is happening to a less complete state, and we have increased pore size materials. So here you can see with a grayscale of 45, we still get a fairly dense material, but we can still see some pores in there. With a grayscale intensity of 75, we get really, really big micropores. So we initially did quantify that by printing little squares at different grayscale intensities. Here we've got the whole area, and we could see that between grayscale 0 and 75, we could actually print objects. If we went beyond grayscale 75, we wouldn't be able to form any material anymore, and our printed structures would simply wash away. So you can see the digital light projection. You can see the light coming from the LED array. In this type of printer, it's then a phone screen that opens and closes certain pixels to allow the light through. Then we've got the grayscale mask that digitally is applied, so it's a setting that you change in the computer. And then it is similar to changing the intensity of your phone. If you're in a dark environment, you don't want your phone to be really bright. But if you are walking out in the sun, you want to increase the intensity of the phone, because otherwise you can't use it anymore. This is a phone scale as well. So this grayscale tunes the intensity of the light that's coming through. So again, grayscale 0 got a dense material, grayscale 75 we got a highly porous material. And if you look in here, it is because you get increasing amounts of the monomers being incorporated into your polymer structure, where with the 0 time scale there is hardly any through pores there, and we get a more and more open structure being formed by polymerization using the grayscale mask. If we look at the characterization, we can also see that the pore sizes of these materials at a grayscale of 75, we've got a pore size relatively narrow, around 50, whereas with the grayscale 75 mask, we have a lot less light, which means that we get larger pore size, but also a much broader pore size distribution. And again, we have the same trends that with the more intense the light, the lower the porosity. So we are, if we have a 0 grayscale, we are at a porosity that is very close to our resin that doesn't contain any porogen, and our geometrical density, our materials get more dense with our grayscale mask. And there's a fair difference in our density between our grayscale 0 and our no porogen containing resin. But other than that, the trend follows what we expected. So we then looked at wicking. We created some test structures to see, we know that wicking is a function of the pore size, because we use the surface area. The charged surface is hydrophilic, as well as the knowledge that the finer the pores, the bigger the flow resistance, and therefore the slower the material will form. So we have a test device here. This is the mask that was used for printing the devices themselves. Whereas here you can see the grayscale mask, where you can see that an intense grayscale is applied with grayscale 75. So that vial will receive a very low dosage of light, and therefore will have very large open pores. And we've got our grayscale 0 as a control sitting next to it. This is the way that the devices looked when they came out of the printer. Again, printed, no exchange required. We only use one resin in the printer. We had different amounts of fluorescent solutions, grayscale 75, grayscale 0. And after 8 hours, our reservoir with the most porous material had wicked all the way through, whereas both our grayscale 45 and our grayscale 45 showed a little permeability, and our grayscale 0 was indeed dense, and we couldn't see any wicking of the material up in there because it was non-porous.
Wicking is by capillary action? Or
Yeah. So capillary action through a porous material. So here we can see the wicking distances where increasing grayscale means less light, means higher porosity, has got the highest wicking distance, whereas our grayscale 0 doesn't wick at all, and therefore we can consider it being non-permeable. So we then decided to make a quick colorimetric test to see if we could use this device for the detection of iron in soil. So we designed 2 different reservoirs to be in there, have our microfluidic device printed from the dense material because we don't want our sample and our reagent to wick away into our device. But we did want a porous membrane in the middle in order to separate our soil sample from our reagents. And then we hope that our analyte and reagents would meet inside the porous membrane, and then using a colorimetric reagent we would be able to see that. So the can see a little bit that we're overexposing. So here you can see that the interface between the dense and the porous material, there is a little bit of a step because our material expands a little bit on the area where we have the interface between overexposed and underexposed materials. Here you can see the step in a little bit more detail, and we believe there are some thermocapillary effects that actually pump fresh pore agents to the interface, because when we have a higher light intensity, we also have a lower viscosity and we create some flows. So we believe that we've got a thermocapillary effect that actually recruits more monomer to come to the polymerization site, and therefore we get slightly higher features formed at the interfaces rather than in the middle of the devices where there is no monomer to be recruited because it's used everywhere. The other thing I quite like about these profilometer images is that you can see that we're doing digital light projection, so you can actually see each of the pixels back. So you can see here we're looking at a 200 micron. We've got around 30 micron pixels, so you can see, recognize the high light intensity at the center of each pixel, making these graphs. So we looked at the SEM of the interface though, and even at the interface the layers are very nicely adhered and stuck together. And we ultimately applied these devices for the detection of iron from a soil sample. So here we have the devices. We introduced the soil sample with some, I think it was nitric acid to reduce the iron 3 to iron 2. We put that into the left-hand reservoir. We added a phenanthrene solution to the right-hand reservoir, and then just waited for 10 minutes to allow our iron 2 to permeate, diffuse through the membrane towards the phenanthrene. And at the same time we expect our phenanthrene to do the same thing in opposite direction. And indeed at the interface we can see a pink line being formed because the iron and the phenanthrene find each other. So in absence of iron we didn't see any pink color, and with increasing iron concentration we could see an increased pink intensity, and we could quantify this by image analysis using image J, where you get the intensity of the pink zone here on the y-axis, the concentration of iron 3+ that for the assay was converted to iron 2+, and you can see a nice linear relationship between the color intensity and the amount of iron. We didn't think we would be very quantitative, but we compared the results with ICP-MS from the same soil samples, and we were within 2% of the the amount of iron established by ICP-MS. So we were quite pleased how well this assay worked. So through this work I hope that I've demonstrated to you that digital light projection can be quite effectively also used for the integration of functional materials. First thing, we established that by addition of a porogen you can actually change your dense resonance printing dense materials to render them porous. There's different parameters that we have to play with to tune the porosity of the materials. Some of these parameters are in the resin chemistry, It is the monomer concentration, the porogen concentration, the photoinitiator and the photoabsorber. So at the interplay of those parameters, we can tune the porosity, where the photoinitiator allowed for reasonably fine tuning of the porosity, whereas the porogen was our big dial that could get us to an order of magnitude difference in pore size of our materials, as demonstrated with the size mobility trap for the DNA extraction. Printing parameters play a role as well, so we can tune the exposure time, but also with the grayscale mask the intensity of the printer, and other parameters we can use to manipulate the pore size of the printed materials are the layer number, the number of layers that are being printed, as well as the layer height. So this was the functional integration by digital light projection 3D printing. If you've got any questions, then I'd suggest, you've got a question, great.
Not much. A slide before that, where you are talking about the, yes, it is by osmotic, how it is going in that? You have a membrane in between?
Yeah, so.
One side you have sample?
Yeah.
And other side it is?
Phenanthrylene solution.
Okay, you are getting a color because of this complex formation.
Yeah.
So, how you are controlling the movement?
It is just wicking, so
Wicking.
just wicking. So you use the wicking and you start off dry and the reagents from both sides wick in, and then they meet each other. And once everything is wetted, transport is by diffusion.
So I was thinking, as if you have a membrane, it is just osmotic.
Yes, there could be osmotic. So we haven't controlled the osmotic pressure, so there could be osmotic pressure driving fluids as well.
Pore size of the ion moving and the membrane. That are other parameters to be taken care of. No? Pore size of the membrane, you know.
Yeah.
How whether those ions can diffuse through those membrane, that membrane.
Ion.
Size of the ions, pore size of the ions, that will also matter.
Yes, but in this instance, the pore size is a couple of 100 nanometers, so the ion has no problem diffusing through.
Okay.
So the only time that we've worked with the relatively dense membrane was in the size mobility trap, where we ended up smaller than 20 nanometers, and that's when you start being able to select to differentiate between the transport of larger molecules and smaller ones. But these holes are so big that the ion and the phenanthrylene had no problem passing through the pores. This is not a small pore size material.
They are vertically placed, or they are vertically placed?
It is printed in 3 dimensions, so it is.
Sir, microfluidic chamber create
So this is the device looking so vertically. So we've got about 1 millimeter height between the bottom of the reservoir here and the edge. So it goes down. It is like 2 little cups with a barrier sitting in between.
How the mass affect the pore formation? How the mass affect the pore formation?
Yeah.
How the mass affect the pore formation? When we increase the mass, how pore will be formed?
They are not playing with the mass.
Actually,
मास किस चीज का?
Slide में दिखाई थी. We got 0 mass and 75.
Yeah, GS.
So that's the grayscale mask.
Yeah,
so
they are just asking about that.
So the
grayscale 75 and 0, they are managing. They are being managed.
Yeah, so they change the light dose that is given in the light intensity. So if you have a very high light intensity, you get a lot of places where your oligomers, your polymerization nuclei form, because you've got a lot of your photoinitiator that is activated all at once. Whereas if you've got a lower intensity, you've got fewer nucleation sites. So you get a very different formation of your oligomers because your formation rate of your radicals will be different. So we were playing around with the polymerization kinetics by changing the amount of photons that you throw per unit time at the photoinitiator. And
how they are affecting the interaction of the ions? phenanthroline and iron. They are
They don't know. Iron and phenanthroline are stupid molecules, and they are just introduced into a device that they don't know how it was made. So we first make the device,
okay.
and then we use it.
Okay.
So iron and phenanthroline just see a membrane as if we had a reservoir with a bit of paper in the middle. They don't know how the membrane was made. They just see something, it's porous.
Okay. Based upon the pore size, just the
Yeah.
detection was done.
Yeah. So it is just a material. That it is just a material that has a pore size that is small enough to stop the dirt. Where's my picture? And the only reason that we've got a porous material here is that we don't want the soil to be moving into the place where we are detecting.
Okay.
So could we have done this by just clamping a bit of paper? Yes, we could have. But then the device would have needed assembly to put together, whereas this device didn't need any assembly.
When we are using 110 phenanthroline, iron 2 is the main, which complexes is it?
Yeah. So the student was not a chemist, so he made up the solution as an iron 3 solution. We had nitric acid present to reduce the iron 3 to iron 2, but the calibration curve, we contemplated changing these concentrations all back to iron 2, but then they become really just slightly different numbers, and we're like, let's just say that we made a calibration curve making up the different solutions at the iron 3 standards, and then we had nitric acid present here to reduce the iron 3 to iron 2, and we made sure that the nitric acid concentration was the same. So he should have made iron 2 solutions and done the calibration that way, but he didn't.
Specified in this case, na,
No,
rather
then,
than
for total iron, ascorbic acid or something, so that iron 3 is reduced to iron 2.
Yeah. So the reducing reagent was in there, but he omitted to do a separate calibration where we made up iron 2 solutions, which would have been the thing that he would have needed to do here to make a nicer calibration curve. So
for ICP
good pickup, that was indeed, and yeah, we looked at ways, but we then thought it was most honest to just say we made up the iron 3 solutions and measure the color, because we couldn't, we had no way to confirm that we always had 100% conversion of our iron 3 into iron 2. So we asked him, where is your calibration directly using an iron 2 solution? And he said, huh? I just took the iron and I followed the protocol. So that's when you get an engineer to do a chemistry project.
So, and another thing, ICP-AS, you have specifically used iron 3 for ICP-AS. You have also
We've used the same sample. So we've used the soil sample that we...
no, standard curve. You must have standard calibration on the basis of which this.
I assume they have done that with iron 2, but it's a separate...
Normally for ICP, total iron comes.
I haven't done the ICP-MS. We gave the sample to the department, so we just handed in the sample and we
So I have worked
got
with
back the
ICP-MS,
concentration.
That's why I'm saying we normally got total iron.
So,
We don't have
but
separate
it doesn't
iron
matter,
for
because if you reduce all your iron 3 to iron 2, it doesn't matter, because you end up measuring total iron
Total
anyway if you reduce it all
yes,
down.
Yes.
Yeah, otherwise, if optical density is measured, then it
Then we can distinguish iron 2, iron 3.
Yeah.
Using
That-
spectrophotometer at a specific wavelength.
Yes, but we don't have the volumes here to do that.
Okay.
So,
Okay. That needs
so
to
for
be-
confirmatory analysis, the lab next door had an ICP-MS and an operator. So we had our soil sample and we just said, you do that and let's see how far we're off. And we're hiding under the table thinking we'd be 20, 30% off. And we're really pleased that we ended up with the same numbers. But the paper has got all the detail in there somewhere how the ICP-MS was done, but I honestly wouldn't know.
Okay.
what is the role of 110 phenanthroline? Means basically, if I say there is a wicking of iron and we are using ICP-MS, ICP-MS will understand the metal ions in all.
They have just verified that binding. ਉਹਨੂੰ verify ਕੀਤਾ ਹੈ, quantify ਕੀਤਾ ਹੈ using ICP-AS.
Yeah. So the iron
Quantitative
testing was just the easiest demonstration we could think of a chemical assay that could benefit from having a membrane barrier inside a reservoir.
Yeah, my question just driving force, if I say it is a wicking action or capillary action, then iron is moving from one to the next. Based on equilibrium, it will be setting up certain concentration on the second one. Since you have certain concentration in the sample,
Yeah,
first one, it goes to the second one. Some equilibrium is set up in the second,
yeah.
based on the initial concentration, and you are able to know, be using ICP-MS the concentration, what calibration we are making. You have
We have kept, so we haven't considered the drive of concentration gradients, but we have fixed the time to take these photographs in order, so the color intensity would indeed change with time, because you'll get increased diffusion of your phenanthrene into your sample reservoir and diffusion of your iron into the other reservoir. So we fixed the time to then
Concentration of the iron solution.
yeah.
You must have taken known concentration of iron solution, no? That you have
Yes, for
put
the
into
calibration
that.
curve, yes.
That's what you have verified from ICP-AS. That concentration was verified.
The concentration that was verified was the concentration of the unknown in the soil sample. So we got a soil sample, we split it into two parts.
Okay.
One went for the microfluidic
Okay,
testing,
okay.
the other one went to the ICP-MS. And then we had some other soil that we had on campus that we confirmed with ICP-MS that it was the amount of iron present was negligible, so it was under the sensitivity of our assay. So our calibration curve was also made in presence of a soil sample, but one that we knew that didn't contain any iron. So our calibration curve was made with a soil that we know didn't have any iron in there, and our test sample came from a mining site that we knew would be high in iron.
Sir, the question on the question.
It's done.
Specifically unknown sample वास्ते कितना just ਉਹਨੂੰ verify ਕੀਤਾ 110 phenanthrene ਦੀ ਵੀ concentration vary ਕੀਤੀ ਹੋਏਗੀ sir 110 phenanthrene ਦੀ ਵੀ concentration vary ਕੀਤੀ ਹੋਏਗੀ that would have taken all the iron for binding ਦੋਨਾਂ ਦੀ concentration ਤੇ play ਕੀਤਾ ਹੈ ਮਤਲਬ sample unknown ਹੈ ਪਰ ਉਹਦੇ ਨਾਲ multiple 110 phenanthrene concentration might you have varied.
No,
No,
we've optimized it, but then didn't vary it during the assay.
Optimize.
So we ensured that we had an excess of 110 phenanthrene to make sure that all the iron was being bound
Yeah,
and therefore
this is what-
caused the color.
That is always taken slightly excess.
Yes.
Yeah.
It is always there.
Yeah.
Then only we can have the calibration.
Yeah.
ਉਹ ਬਸ ਉਹਨੂੰ verify ਕਰ ਲਿਆ
So our only varied element was the concentration of
Yeah.
iron, and not
Yeah.
both, because then you don't go anywhere. So we did lock in.
But optimization was needed.
Yeah. Okay, stretch our legs before we go to nanoparticle synthesis. I'll give you a little bit of a break. Was it nanoparticle? Yeah. Oh no, organ. So let's see what the program said. Do we do organ on the chip first, or? No, we do nanoparticles. So please stretch your legs, because there was a lot of information and we now need to completely change gears. We're not going to do anything 3D printing anymore. We're going to rewire our brains to look at how fluidic phenomena have been used in nanoparticle synthesis. I'll be as much in the... I think we need to help each other here. So I'm not a synthetic chemist. I've never made nanoparticles. Just for preparation, I knew that a lot of you were working on nanoparticles. I know there's people using microfluidics, so I went through a couple of review articles and lifted out some examples that I thought were relevant, where they combined microfluidic phenomena to get it to benefit the nanoparticle synthesis. So it is for you to say if this is good or not. I don't know enough and couldn't read up. I only had Sunday to do this. So you will understand the chemistry and you will know the differences in the lab. I understand the fluidics that have been used, how to incorporate microfluidic mixers to enhance the nanoparticle synthesis. So if you've got any question on the synthesis, the answers are probably in the papers that are referenced there. In my naive point of view, any nanoparticle is a sphere or a star-like object, and they could be polymeric, they could be inorganic. For me, from the fluidic perspective, they're all the same. For you, from your project application perspective, they're certainly not the same because there will be very different chemistries at play.
Yeah. One question is, while developing all these applications using microfluidics and 3D printing devices, if you can just give an idea of the characterization tools required for your for catering the desired application. So can you give an idea? Side by side I have asked few, like you said, porimeter for determining the pore size.
I think the characterization depends on the assay. So it is really hard to, because if you don't have a porous material, you don't need to have any characterization techniques that measure porosity. If you don't use a fluorescence detector, getting the spectral properties of your material is meaningless. So it depends on your application, what the characterization is that you need. If you want to do fluorescence detection with excitation at 4 or 5 nanometers, at that point it really becomes important that you characterize the absorption spectra of your materials. Because a lot of polymers will be absorbing at least at a 365, may still be absorbing it at 4 or 5 level. If you have a coulometric reaction where you measure the absorption at 550, your characterization at 405 doesn't really matter. If you don't do fluorescence, you don't need to assess autofluorescence. If you want to do fluorescence detection, it's very important to ensure that your material is not autofluorescent at the wavelength that you're working at.
So complementary based upon the behavior of your porous material as well as your analyte which you want to detect, the characterization tool has to be selected.
Yes, so in the development of the microfluid, in
membrane, porous membrane, material nature, your analyte nature. So based upon their properties, you will have to choose the characterization techniques.
Yeah. And sometimes you just have to get by because there is no good characterization techniques.
Yeah.
So we looked at some inkjet 3D printing to create filters.
Okay.
And we couldn't get any proper measurements out of the mercury nor the perimeter.
Okay.
So we ended up just buying a whole range of different particle sizes and looked with the microscope which came through. So we got particles of changing size, and each of the particles had a different fluorescent color.
Okay.
So we just got the particles into the device, confirmed we had what the distribution was of the 4 or 5 different colors we had on one side of the membrane, looked at the other side of the membrane, which are the particles that are present. Orange is there, and that means that 100 nanometer particle gets through. We don't have any pink there, that means the 2 micron particles haven't come through. So we looked for a very long time to a more traditional characterization technique. SEM is not really quantitative,
No.
but these materials also really charge, so we couldn't see anything with the SEM. So we just look around, what do we want to know? What do we have available? And sometimes we end up with the really low level things like we get ping pong balls, different colors, different sizes, and see who comes through. It was the best we could do. So there is no standard approach because
Yeah.
it all depends on where the novelty sits, what you need to characterize. So
Yeah.
we needed, in this work, we needed to do a whole lot of perimetry because the novelty of our work was the making and understanding the processes underpinning the synthesis of these porous membranes.
Yeah.
So we couldn't have done this without a perimeter.
Yeah.
Now this is established. You can just say, we used membranes as published blah blah,
Yeah.
and used for application, and at that point you don't need to do any perimetry anymore.
Yes.
So it depends on where you sit in the innovation cycle,
Yeah.
what parts of your device you need to characterize, and which ones you don't. Because poor Harry, I think 2 years of this work was just characterization. He kept on doing, he made thousands of membranes and had to just look at the pore size all the way through and then try to find the trends.
Yeah.
But that is because the scope was, how does the formation of these porous materials work? Okay, let's see how far we come together in nanoparticle materials. So I've already shared a lot of these slides with Professor Malik, and I'm sure that by the end of the course I'll give the updated of the last changes that I made. And you'll get all these slides and with that also the references. So there were 2 different review articles that are recent and I thought gave a really good overview of what has happened in the field of nanoparticle synthesis. This one here, the performance evaluation, was much focusing at the synthesis of polymeric nanoparticles for drug delivery. Hence they've got the performance evaluation in there as well. But they also described really well a quick summary about the microfabrication aspects that we also discussed, as well as the fluidic aspects and the importance of mixing in making these materials. Other review here is particularly looking at the oxide-based nanoparticles, looking at the inorganic ones, and look how using microfluidic technologies and using the enhanced control and control that you've got on the mixing at the femtoliter volume, how you could use that to create the oxide-based nanoparticles under milder conditions that than they're normally used in the lab. So you can see that there's low temperature solution-based methods, and you can make it in continuous flow pathway. Why would you think about doing microfluidics if you're making nanoparticles? The reviews is because you've got good control of the fluidics. You've got very good control on the mixing, which means that you get a very good repeatability between different batches. Haven't done it myself, but all the papers that I've read, they compare the pore size distribution with the same nanoparticles that were created in bulk. And typically the pore size not the pore size, that was previous lecture. The particle size distribution, the monodispersity, is higher when the nanoparticles are created using a microfluidic device than they are when made using a bulk method. This is all thanks that we get enhanced and repeatable mixing. Another reason for doing microfluidics is if you've got expensive starting materials. Because you can, using very small volumes, make a batch, characterize it, and optimize your methods even further. So you can reduce your cost. You don't need to heat as much, even if you want to have your nanoparticle synthesis happening at an increased elevated temperature. The mass that you have to heat is a lot smaller, which means that your energy requirements are lower, and you've got a decreased volume of reagents that you need to use to make a small batch for evaluations. By controlling your flow rates and your flow rate ratios, you've got an opportunity to automate your variation of your reagents, and therefore you can make analogs. So you can have different reservoirs of your reagents plumbed in. You scale the pressure ratio if you use a pneumatic system, which means that you change the flow rate ratio of your different reagents, which means that you change the concentrations. So you can screen through a large range of different conditions to optimize your optimum to establish your optimum for the formation of the nanoparticles with the characteristics that you want to achieve. So you start off with a 1-to-1 ratio, collect the particles, you change your ratio to 1.2 to 0.8, you collect those particles, and you do that over and over again. So in the morning you can actually collect a whole range of nanoparticles that have been used under different concentration ratios of your reagents. They are relatively simple to operate. You can just change the settings of your pump. Talked about the fact that we've got pneumatic pumps where we change the pressure in the bulkhead above the liquid level. There are syringe pumps, there are peristaltic pumps. If you don't have any pump in your lab, gravity is a great pump as well. So you can just have your reservoir half a meter above your microfluidic device, and then gravity will just drive your flow. Can't get really high flows using gravity, but if you want to try something out, it is actually quite effective as well. By working at microfluidics, the flow resistances predict everything. So it is very predictable, and therefore you've got a high control of the experimental conditions. And it provides you to tailor the opportunities, see what particles you are making under certain conditions, see how trends change with your concentration ratios, and that way you can optimize the size, the shape, and the functionalization of your nanoparticles. Last thing is that we are not very good at manipulating picoliters by hand, which means that we control everything with different pumps. Pumps are typically really easy to operate electronically. So you can program your syringe pump to ramp up or ramp down flow rates, and then at intervals after it has operated at flow rate, collect all your particles. So you could even have your syringe pump going through a program, collect your nanoparticles every 2 or 3 minutes, and have a nanoparticle created under its unique conditions in every time frame. So you can, rather than having to make up reagents in a whole range of different mixtures, you can use your flow rate ratios to change the ultimate concentrations that are present once the nanoparticles are being formed. Lots of different nanoparticles have been made, which is where I got lost in all the reviews. So we've got metal oxide with alloys, core shell particles, polymer particles, nanocomposites, quantum dots. I think any particle that has been made with a bulk method has also been made with a microfluidic method. It is just a toolbox, and you can apply the tool to a whole different range of applications. I know you all thoroughly enjoyed the first week that we started off about physics and mixing and laminar flow. This is where it comes back, and this is where it gives advantage to nanoparticle synthesis. So we've got the conventional approach where you quite often have dropwise addition of the reagent into a stirring beaker. And then we've got the microfluidic approaches where we have single phase, when we have miscible solutions, or we've got multi-phase flow where we talk about immiscible components. So we've got an oil phase and a water phase. We can have 2 ways when we've got 2 different inlets, and one. My batteries run out. It's fine, I'll use the one in PowerPoint. So we have simple devices that just look a Y shape where we have one interface. If we create 3 different inlets, we kind of have 3 different interfaces, and we can create a diffusion interface, which is useful because if we here have water and acetone, we create our nanoparticles here through nanoprecipitation. So we have our polymer that really likes being in the acetone environment, and it is happily dissolved in there. We introduce it into our microfluidic device where we've got our acetone and water flowing next to each other. Through diffusion, we get increased concentrations of water in our acetone phase. This means that as the acetone and the water mixes, the polymer actually isn't as well dissolved anymore, and it starts slowly precipitation. So we start off getting some nucleation, And with time, the concentration of water in our acetone increases because we've got more and more water from our sides diffusing in, and we've got more and more of our acetone diffusing to the sides of our channel. So we continue with our nucleation, and then at the point that balance is achieved, at the point where we have full diffusion, full mixing of our water of acetone, then the solubility of our nanoparticles doesn't change anymore, and we just end up with the particle size that it is. Here we've got the a process described where a microfluidic has been used to introduce PLGA pack polymer nicely dissolved in acetonitrile. We have got water coming in here from the top and the bottom. You can see here the amount of the acetonitrile solution is really hydrodynamically focused and pinched down to a really small stream. So we can get rapid diffusion of our water into our acetonitrile phase, very quickly create the solubility challenges, get nucleation to form and the formation of the particles happening. So here we can see a photograph. Don't have this size here, but of the microchannel. So I don't know what the scale bar is, but I assume it's like a 50 or 100 micron microchannel. We can see that the acetonitrile solution comes in. You can see the phase boundary forming here with the water. You can see that we've got a focus stream where our nanoparticles slowly precipitate out. And here you can see an SEM of the nanoparticles, and you can see the particles are 30, 40 nanometers in size, so it's probably TEM, but you get a relatively homogeneous nanoparticle formation and using a very simple device. The size here is not critical that it's very small, so in principle you could make this device using any polymer that withstands acetonitrile. A slightly more complex two-phase approach is used here, where we make a core shell particle. So initially we have a first microreactor here where we mix the flow of our solution C was our titanium. Yeah, so we've got titanium tetraisopropoxide, that's where I need your chemist to pronounce that, in isopropanol, mixed with ammonia. So we get nucleation of the titania particles and an aggregation of the nuclei. Here we've got, there's indeed our solution, our TIOS, I've used that before, with our ammonia. Nothing much happens here other than the mixing, but if we add the aggregated titania nanoparticles together with the basic TIOS solution that has already started to produce the TIOS from memory, we then can encapsulate, grow a silica mantle core cover around our titanium cores. If we look at these particles just under a photograph, we can hardly see that they're in solution. So here we can see an Eppendorf cup with just some water and with the particles made using this two-step reaction approach. And you can see that with the eyes you can hardly see them, and the average pore size that was determined for these nanoparticles was 38 nanometers. You can see some TEM images, and as you can see that the particles themselves, they are nicely monodisperse. Here we have relatively short microchannels, so mixing is only impacted here by the diffusion rate. But in nanoparticle synthesis, mixing makes everything better. Anything that I've learned is that the better performing microreactors for making nanoparticles all have enhanced mixing functionality in there. So here we've got some polymeric nanoparticles being formed where they haven't only allowed time for mixing by creating a serpentine channel. Remember the first week we talked about one of the problems in microfluidics was the mixing, And one of the ways that we could allow for better mixing was to make the channel longer. If we want to make the channel longer but our chip not any larger, then the serpentine channel was the solution. In this article, they've done that even further. They included the herringbone mixer with the little like traffic humps on the bottom of the channel. They included those on the bottom of the serpentine channel to get the solutions to create the convective flows, to get the mixing of the different reagents to happen faster, and therefore they could get nanoparticles with better properties. We did talk about the fact that we had active and passive mixers. So the herringbone mixer is one of our passive mixers, where we use microfabricated structures in combination with the flow to create certain flow patterns that then will facilitate our mixing of our reagents. Who remembers what we needed for an active mixer? With an active mixer, we needed an active source and an additional source of energy to facilitate our mixing. So we have stir bars, we have magnets. In this case, we mix using an acoustic field. So we put a little speaker next to our, so literally we've done it with speakers that we've taken out of speakers to play from our iPods. So put a little speaker next to our microchannel. If we have a bubble, we get the acoustic waves to do funky things, create swirly whirlies. And here you can see what actually happens if we look at the streaming of particles. So here we've got some fluorescent particles in a microchannel in a flowing system. And you can see the streamlines. You can see when the acoustic field is applied. You can just see the contours of the droplets here. You can see that there's circulatory flow. You can see the nanoparticles over the fluorescent particles that were introduced in this microchannel. They're moving around. So if we're, instead of having fluorescent beads in this microchannel, if we have two different reagents, we've got a polymer dissolved in a good solvent, and we've got the anti-solvent, then these twirly whirlies will create a big vortex micromixer. It will be like a big whirlpool in a swimming pool. It will mix it all around. So here we've got little bubbles being present, because bubbles are really good for focusing these acoustic waves into areas, into these flow patterns. And we can see that at each of these dots we get really, really good mixing. And we've got the flow, the convective flow happening that allows for very quick mixing of our solvent with our anti-solvent. And therefore we get the formation of our nuclei and the growth of our nanoparticles. Because under a very small distance and a very quick time frame, we go from a two-phase solution into a homogeneous solution where the solubility of our polymer is significantly lower than it was when it was present in our solvent. So we get our nanoparticles being formed. This acoustic device was applied to two different types of nanoparticles. One of them were PLGA PEG nanoparticles, and the other one were some liposomes. So it was exactly the same device where they just introduced two different sets of reagents. And what they found is that if you start off with lower concentrations of your polymer, you get to smaller nanoparticles. And if you go at higher flow rates, which is where probably you want a good pump rather than just gravity fed, your nanoparticles get smaller the higher flow rates become, because that mixing time becomes faster and faster.
Lower characterization was done by using particle size analyzer?
Yeah.
And upper one?
I don't know. I expect that these are the extracts from this data. So I think it's all with the particle size analyzer, and this is just a different plot.
But we don't get any flow rate in...
That's a different experimental conditions. So they've used this device where they introduced the reagents. So they did one experiment, there's my mouse, one experiment at 10 microliters a minute. So each data point here is a different series of experiments. So they may have done them with the same reagents and just collect the first particles made at 10 microliters a minute. Increase the flow rate. next experiment, increase the flow rate, increase the flow rate.
Right.
Do that all for the 5 milligram per milliliter solutions. Clean your device, do it again with a concentration that's 2.5 milligrams per milliliter. Start off at 10, go higher and higher in flow rate, and collect your particles at the exit of your microchannel, and do the characterization on those materials as soon as you've produced enough material that your characterization method requires. So here the only microfluidic is the synthesis, and the characterization is all done using standard equipment. We talked about the Dean flow by having the circular devices where we could have big particles under certain flow rates concentrating at one side of the microchannel, small at the other. And if you think back then, the Dean flow in the circular channels, there were the fact that we had opposing flows at the top and bottom of our microchannel taking place. So in this article they used that to have a very quick mixing of 2 different reagents. So we have TIOS coming in at one side of the microchannel. So we've got 2 inlets here in our spiral microchannel. One introduces the TIOS, the other one the surfactant CTAP in form of micelles. And you can see even only half turn into that microfluidic device, the boundary between these 2 solutions already can't be recognized anymore, because those counterflow, Dean flow that is happening in a spiral device where we are flowing straight on, but we still get vertical flow lines, flow patterns happening because of the curvature of the microchannel. And having those mixes happening in opposite directions means that we get very quick mixing of our CTAP and our TIOS. So we have TIOS dissolved in ethanol as one of our reactants, present in, and the other reactant contains ammonium hydroxide as well as CTAP as a micelle. In this instance, a syringe pump was used, and the flow rate that was used was 400 microliters a minute. What happens is that we've got the TIOS present in pure ethanol and the CTAP micelles that were diluted in ammonia. So they mix here at the interface. As soon as the ammonia hits the TIOS, we get the hydrolysis of the TIOS here at the interface. And that then is followed by the condensation of the hydrolyzed TIOS to build a shell-like particle. So we get the 2 reagents to meet. At this interface here, the TIOS is directly getting hydrolyzed by the ammonia that's present in the CTAP. We get the micelles to form a layer around that, and then we get a condensation reaction. And here you can see the way that the nanoparticles form. We start off with an interface here between the 2 different solutions, and very close, half a turn from the injection point, we already can't see that phase boundary anymore. So here we've got some idea of the types of particles that can be formed using that way. Here, the scale bar here is 200 nanometers, so they're relatively large particles, but they're beautifully monodispersed. You can see here the particles are about 1,000 nanometers that were created in this instance. And here on the TEM you can see that it's a very nicely monodispersed distribution that was being formed. So Dean flow probably was not most interesting to hear about the mixer and the particle separation, but you get kind of an inbuilt mixer in your flow. If instead of your microfluidic device, you design it in a straight line, you design it in a curve, and that way that you get the additional mixing elements, which allows you for the synthesis of really nice particles. Microfluidics, it's a physical phenomenon. It doesn't mean that you need an expensive clean room facility to create your microreactors. And here we've got a very nice example where microfluidic phenomena have been used and simplified to simply use some capillary tubing to do multi-step nanoparticle synthesis. This is a photograph. This is just some polymer tubing that, particularly if you have an analytical laboratory, you'll find all over the place. From HPLC and all kinds of post-column, pre-column reactions, we've got a whole range of Y pieces, T pieces, 6 port crosses. There's a whole range of plasticware available that allows us to combine different tubing in different configurations. So in this instance, there was a 4-way cross device was connected with 3 different reagents and an outlet. Fe2Cl, so some iron chloride, some mineral oil, and some base. Were added together because we've got 2 aqueous solutions and an oil phase will be forming droplets. If we use a hydrophobic tubing, our oil phase will be our continuous phase because that will be wetting the surface, and we'll have aqueous droplets present in the oil phase. These aqueous solutions, we've got both our ion solutions coming in and our ammonia. So we get the formation of our first part of the nanoparticles taking place because of the high pH. We then sequentially can mix at elevated temperature, simply put the tubing in the oven. Here we don't have any fancy herringbone mixers or anything happening. We've just got a coil to allow diffusive mixing to take place. So these aqueous droplets, they're kind of bouncing around, causing a circulatory flow while they're flowing through the channel. Here there's just some length, I think about ½ meter or so, of tubing that has been coiled together as the first stage. Then there's another T-piece where the first reagent can be added, allowed to react for a little bit shorter, second reagent, third reagent is being added, and then the nanoparticles can be collected at the end in a small Eppendorf tube. And here we can have some feedback control to change the composition of the reagents to optimize the nanoparticles to what we want to do. In this instance, they made some core shell particles, so they looked at different conditions, what the thickness was of the core that was made, what the thickness was of the shell, and what the size was of the overall particles being formed. And you can see that we have particles here. The core diameter is around 6 nanometers. We've got a shell thickness of about 6 nanometer, and the total size of the nanoparticles is just over 12 nanometers. So we get, with a very simple setup with just some bundled up bits of tubing in a 70-degree oven, so it doesn't need a lot of equipment to do this, could actually get really nice monodisperse core shell particles with controlled properties of the core and the shell. So that was already using droplet microfluidics. Just to remind you, moving on to a different regime, is that we have our single phase flow as well as our droplet phase microfluidics that we can use to make our particles. So in this instance here, we've got an example where we've got some a reagent and some precursors that we can mix together before we add our continuous phase. We allow our mixing to happen in the droplets because we've got the circulatory flow happening, and we can collect our inorganic nanoparticles if these seed precursors and the reagents were tailored towards inorganic nanoparticle synthesis. We can collect them on the other side of the tubing. We can do this in all kinds of different geometries. So we can add 2 different reagents and have them added to the oil. We can have one side channel that introduces all our reagents at the same time. We can add reagents sequentially, where we first form our droplets like this and then add the reagents. We can have little mixers where we mix 3 different reagents in different ratios through the control of the relative flow rate ratios of these different reagents. Get them to come together into a little vesicle that self-mixes through the rotation in the flow. We can use electrodes to impose electric fields to bring reagents closer together and make reactors that way. Instead of doing in microfluidic devices, we can plumb different parts of tubing together and make the nanoparticles different that way. And we can add reagents sequentially, where we've got a reducing agent, a gold salt, and another solvent, and get them to form droplets and have our nanoparticles formed in the interdispersed phase, using these the movement of these droplets again to enhance mixing in these systems. So here we've got 1 is our continuous phase, 2, 3 and 4 are both aqueous reagents that are first added together. You can use the difference in the flow rate ratio between reagents 2, 3 and 4 to change the reagent composition of your aqueous phase coming in. Aqueous will be the dispersed phase, so we'll get droplets of any combination of 2, 3 and 4 being formed, and then mixing itself and create different particles. So here again some TEMs showing really nice monodispersity. In this instance our diameters are around 4 to 5 nanometer diameter, and these were gold nanoparticles, so characterization was also done spectrally. And here you can see that where's C and D? C are the particles that are made using the microfluidic reactor. D were the ones that are created in bulk. You can see here with the one made in bulk, we've got more differences in size and geometry than the ones made in the microfluidic reactor that are shown on top. And that is also reflected in the particle sizing, where we can see a broader distribution and a larger particle size for the particles being made using the same reagents in bulk than has been done in the microfluidic reactor. So that is the why would you go through the difficulty of doing microfluidics? Well, if you just put some bits of tubing together, it is not that much harder, but you get more monodisperse, more uniform nanoparticles being formed if you have control of the mixing and the fluidic phenomena, rather than when you just keep your fingers crossed and you hope the best things will happen in your stirring beaker. So we've got different ways that we can make droplets. So here we can put droplets in droplets. These were structures that were developed for all kinds of assays and then adopted by the nanoparticle community because they were beneficial. We can see a little zigzag channel in order to enhance the mixing. So we've got 2 different aqueous reagents being mixed with an oil that contains some surfactant to stabilize the droplets. After some mixing, we have a 3rd reagent that we want to add really, really quickly, and therefore there's integrated electrodes here to give the mixing an additional boost and allow for very quick incorporation of that 3rd reagent that's added. And here again, you can see beautiful TEMs of highly monodispersed nanoparticle populations. One of the disadvantages of using microfluidics for your fabrication of your nanoparticles, that if you want to upscale, you're not going to work at really high throughput. So getting a vial through or even getting enough nanoparticles for characterization may be a challenge. But then it is important to start realizing that a lot of the microfluidic structures that we make, they have been inherited from the IC technology. And one of the things that's really easy to do in microfabrication is duplication, at least if you create nice microreactors. Fluidics are predictable because our fluidic properties depend on our channel design. Once we've got our channel design optimized to do it once, we can very easily do copy-paste and get multiple reactors to go in parallel. So to increase our throughput, we don't necessarily have to increase our flow rate through our microchannel. We can just have multiple microchannels acting as microreactors in parallel, which has been done here. So they created some curved microchannels in each single unit. They used a couple of wines to have a very efficient mixing at a very small scale. To enhance the mixing even further, like we said before, there were some herringbone structures implemented onto the bottom of these channels to create that circulatory flow profile and enhance that mixing. And here we had, I think, 64 different of these mixers connected to the same inlets and outlets, with a collective outlet for collecting the microparticles. If all these channels have the same size, the flow rates in them will all be identical. And to decrease the influence of very small differences between these channels, this whole device was connected with a much larger flow resistor which allowed for a lot more stable flow between all these 64 different fluidic units. So there were little vias to allow the delivery of the reagents. So a multi-layer fluidic structure was required in order to deliver all the reagent to the mixing units. So in this instance, they did a characterization of the different mixers, and they confirmed that in parallel processing, actually that all still worked. So without the intent of making nanoparticles, they looked at 2 different dyes and validated that they got proper mixing through the herringbone structures after only very few turns. So the solution coming out of a range of different microchannels was all well mixed at the same point. And there were no significant differences. So the parallel measuring in channel 1, 2 and 3 compared to a single channel device, it took a little bit longer for the mixing, but the difference was not significant. And all solutions were perfectly mixed way before the halfway part of the mixing. So the slight pressure drop over the channel, which resulted in a slightly lower flow rate and therefore a slightly longer mixing time, were all insignificant because mixing was still achieved within the first segments of the micromixer, which meant that we got homogeneous particles coming out. So here we've got, I think, 10 different nanoparticle synthesis systems working in parallel. They didn't all do it all in all 64 at the same time because they couldn't get the fluidics right to have 64 separate collection vials. But here we can see that there was not only good monodispersity in each of these individual microreactors, we also get the same particle size and the same monodispersity across our different microreactors that were present on the same plate. So again, we can produce monodispersed particles in parallel microreactors with the same performance as our microreactors would be operating when they are in singular mode, which then means that you can optimize your nanoparticle synthesis very nicely under in a single microreactor, do your characterization, and once you find the optimum, you can outscale by simply having your devices in parallel, which could be in planar using fluidic layering, but I've also seen parallel reactors where they've got 10 on one plate and they then stack different fluidic plates together to get to very similar throughputs as you would get in a beaker, but then using the microfluidic control. So in conclusion, there are a lot of different nanoparticles, inorganic, organic, composites, but most nanoparticles benefit from some level of microfluidic control to achieve smaller particle size and good monodispersity. Mixing is really important, and therefore most nanoparticle reactors you will recognize a mixing element in there. Sometimes these are active mixers, like the mixers that need to have an additional energy input. An example that we looked at was using the ultrasonic waves, so using the sound waves, the acoustic waves, to create the microvortexes to allow for the fast mixing of different reagents. We've also seen a lot of examples of passive elements where particularly herringbone structures are really popular to integrate into microchannels to enhance that mixing. And it is important to notice that in comparison with the analytical devices that we've spoken a lot about in this lecture series, the devices, geometries that you need to make nanoparticles are often a lot simpler to design and make than a lot of the analytical devices that have a higher level of complexity. So at that point when your channel design is easy, your main concern is the material compatibility. So the types of nanoparticles and the chemistry that you want to use. Your biggest concern is what materials would be compatible, and if you've got a list of materials, you can select a microfabrication method that fits your dimensional requirements as well as your budget. So I hope that showed a little bit of how microfluidics can be used for the creation of microparticles, and I'll then have a quick summary as well on agricultural applications to again see how all the concepts that we've talked about in the past week or two get together to applications that are very close to what you're doing in your study and work. So let's take a little bit of a toilet break, and then we'll move on to the agricultural applications. What time are we? 12:20.
As far as the large upscaling is concerned, how much upscaling is possible if we are to cater agricultural applications? We need very large quantities. Can it